If you've ever built a rocket in Kerbal Space Program, you've probably had this happen. You start setting off a rocket, but then it starts tipping over out of control and you can't save it anymore, even with a parachute. It looks ridiculous, but this is actually one of the biggest engineering problems in rocketry. So we ask, why do rockets have fins on the bottom, fuel in the middle, engines in the bottom, and why was the first rocket designed completely wrong? Everything we build depends on one simple idea. A rocket only flies if it wants to point forwards. This was Robert Goddard's first liquid-fueled rocket. It worked, but it was terrible. The engine was at the top with fuel below and it was really awkward. Modern rockets look completely different because engineers learned one lesson, that rockets only fly if it wants to point forwards. Every rocket has two invisible points, the center of mass and the center of pressure. More on that later. A dart flies pretty well, right? It seems like gravity is the only thing acting on it, but really there's much more going on. In this demonstration, you'll see that gravity is simply bringing the dart down while it has a constant horizontal velocity. But there's more going on. A dart is really in a vector field with components of downward gravity and sideways wind, just like this. Then, on the shaft or the back view, if it's rotated, the air pushes the fins and creates a restoring torque. Rockets work exactly the same way. If I put fins on the rocket, it'll fly up and I physically can't make it go east to flip. You'll see it in this demonstration here, where after putting fins on the rocket, I can't move it any more east and it won't flip over. So as long as the center of mass stays in front of the center of pressure, the rocket corrects itself. But if these switch places, then it ends up flipping again. This changes because fuel burns, and the COM moves below the center of pressure for most failed rockets.
So if you take a rocket and try to find its center of pressure, you can tape strings to your rocket and find out where it is by using guess and check method. If it's too far in the front, it'll bend up. If it's too far in the back, it'll bend down. And as you get closer to the center of pressure, it starts facing straight.
Today, engineers use computational fluid dynamics to figure out the center of pressure, but the cardboard trick does the same thing. There's an easier way to compute this using area, but I didn't feel like doing that. Here's my notes anyways. So, we gotta ask, why are fins at the bottom? The fins restoring torque makes the shaft a damped harmonic oscillator actually, so a rocket is really just like a spring. You can see the differential equation there and then the solved solution. I did all the math to figure this out and my notes are in the description if you want to figure out the rocketry equations. Anyways, lift and drag stem from center of pressure and not mass, so we have a torque. Drag is really small, so we ignore it, so the torque is distance from the COM times the force of lift. So we ask, how big of fins correlate to how big of lift? The Barrowman equations give us that. So is this fixed? No, because with crosswind there's a huge torque, but with small fins there's a weak restoring force. Engineers have found the sweet spot to be 1 to 2 calibers. Then we can make calculations for the harmonic damping oscillator here, and we find that, like my physics teacher says, everything in the world is just a spring. So, every time you make a rocket, you're balancing these things and doing all these equations in your head, so it's pretty cool. Every rocket you build is solving this exact engineering problem. Next episode we'll go into why orbits work and understand how we stay in space even though Earth is constantly pulling down on us.